welcome to EC Electronics. Today's video we are going to discuss the concept of resonance in AC circuit. Okay, so we have faced a lot of questions from the RLC network that can be either series or parallel. So one condition that is happening in this series RLC or this RLC circuit is called the resonance condition. Today's video we are going to discuss about the resonance concept, and we are going to discuss the important equations and some problems coming from this area of resonance in AC circuit. Okay, so consider that there is a series RLC circuit. RLC circuit means it consists of three elements. There is a resistor which constitute the R, then there is an inductor, there is a capacitor. So this is a series RLC circuit. So it consists of R, L and C. So this is called an RLC circuit. Since all the components are in series connection, we call it as a series RLC circuit. Right. Now consider that this is driven by a voltage source of value V0. Okay. So this voltage source is driving this resistor, inductor and capacitor. Now if you consider the current I0 in this circuit, the current or this circuit in general behaves like that of a harmonic oscillator. And if you write the current equation for this series RLC circuit, the current equations will be looking similar to that of a harmonic oscillator equation. Okay, and also since there is a resistive element being introduced into this circuit, there we can see a damping oscillation. Okay, so that is all the theory part. Anyway, consider that this circuit is behaving like that of a, or its cara is behaving like that of a harmonic oscillator. Okay, and if you write the equation for this current I0 in this RLC circuit, series RLC circuit, you will get the equation as I0 is equal to V0 by root of R square plus omega L minus 1 by omega C the whole square. Okay, so that is simply voltage by resistance. We are taking the absolute value of resistance, so it is a square root of R square plus omega L minus 1 by omega C the whole square. Okay, so where omega is the angular frequency and this omega is equal to 2 pi into normal frequency f. F is a standard frequency and omega is the angular frequency. Okay, and if you draw the graph for the current of this series RLC circuit, you can see a peak like this. Okay, that is if we are going to draw the current I0 with respect to omega, which is angular frequency, you will get a peak like this. And this, that is, current is going to a peak value at some point. And if you take the frequency at that point, it is omega 0. And this state in a series RLC circuit, or in general, the state in which the current is going to the peak value in an RLC circuit, whether that is a series or a parallel one, is called the resonance state. Okay. So at what particular value of angular frequency, the current is going to its maximum value, and that state is called the resonance state of a RLC network. Okay, and this RLC network has a resonant frequency of omega 0. So we are representing this with omega 0. Generally, we use omega 0 to represent the peak value of current. That is the frequency corresponding to the peak value of current. That is called omega 0. And this omega 0, if you write it in terms of F, it is 2 pi into F0. Right? Very simple, right? Now, what is the peculiarity of this resonance state? So, resonance is a state when the current value is going to its peak value. And we take the angular frequency at that point as omega 0. So, we are actually drawing a graph between I0 and omega, right? So, at one particular point of omega, the current is at its maximum value and we call that it as a resonance state. Okay, so Now, what is the features of this resonance state? In the resonance state, the resistance or the impedance, when we are introducing the inductor and the capacitor, we call the resistance as impedance, right? So, at the resonance state, the impedance of this series RLC network is very, very low. Since the current is high, the resistance has to be low, right? So, at a resonance, the current I0 is maximum and the impedance is minimum. Okay, so the impedance is minimum and the current I0 is maximum. And also another important feature is that in the resonance state, the impedance is only contributed by the resistive element, which is R. Okay, so if somebody is asking you, if some question in which they are being given the resistance or the impedance value of R, L and C, and they are considering the resonance state, and they are asking what is the impedance at this resonance state, means you have to only take into consideration the resistive element. Okay, so at the resonance state, the impedance is only contributed by resistance, or the impedance is purely resistive, not this term. Okay, so this is another feature of the resonance state. And also at the resonance state, even though the circuit is not driven by any voltage source, V0 or any source, this circuit tends to oscillate. This is another feature. That is, this series RLC circuit at resonance condition is having an oscillation even though not driven by any voltage source. So that is another feature of a resonance. So this condition is called resonance state in a RLC network. Okay. Now in the graph, we have mark W0. What is the value of W0 in terms of these elements? The elements are, there is a resistor, there is an inductor, there is a capacitor, right? So what is the value of the omega 0 in terms of these elements? That is R, L and C. Okay, so in order to find the resonance condition, we equate omega L is equal to 1 by omega 0 C. Omega 0 L is equal to 1 by omega 0 C. And from that, omega 0 square is equal to 1 by LC. And omega 0 is equal to root of 1 by LC is the equation to find resonance angular frequency. Don't confuse it with normal frequency. It is angular frequency expressed in radians per second. Okay. So, we have now obtained the value of omega 0. Then what will be F0? We know that omega 0 is equal to 2 pi into F0, right? So, F0 is equal to 1 by 2 pi into omega 0. So, it is 1 by 2 pi into root of 1 by LC. Okay. So, I'll write both the terms here. Omega 0 is equal to square root of 1 by LC and F0 is equal to 1 by 2 pi into square root of 1 by LC. Okay. So, this is the equation for finding the frequencies at resonance. Okay. Now, I hope that you have noted this down. These are very, very important if you are been asking some relations in resonance, or if you are facing some questions in order to answer with the resonance condition. You have these, you need these equations, and also the current equation is very important. Okay, so please note these equations down. I'm only introducing or telling the important equations. I'm not explaining all the unwanted theories. Okay, so we are seeing a peak here. And this peak corresponds to the resonance peak. Okay, so this peak is called the resonance peak. Now, in the resonance peak, if you see, there is a delta omega. Okay, delta omega is the bandwidth of the resonance peak. Bandwidth of resonance peak is delta omega. Now, what is delta omega actually? Delta omega corresponds to those frequencies in which the power, the average power, where the average power is greater than 1 by 2 or half the value of peak power. Okay, so this is the relation, or this is the explanation for your delta omega. So delta omega, if somebody is asking you what is delta omega, then it is the bandwidth of your resonance peak. Okay, so this range of frequencies which contribute the resonance peak, and for those frequencies the average power is greater than half the value of your peak power or your maximum power. Okay, so for all those frequencies this power relationship is satisfied. Okay, and also if you see the peak of this resonance peak, this point or this peak is described by another factor which you may have heard is the quality factor. I have seen a lot of questions asking the relationship or the equation for these quality factors and all. So please note this down. Okay, so the quality factor or Q contributes the peak of the resonance peak on this point. Okay, and the quality factor Q is defined as omega 0 by delta omega. Okay, so what is the value of omega 0? It is 1 by root LC into 1 by delta omega is the quality factor. Okay, anyway, just study this. Quality factor is the ratio of the resonance frequency to the bandwidth. Now, what is the application for this resonance circuit? These resonance circuits are actually used for rejecting a particular range of frequencies. By tuning the network or the circuit to particular resonance value, you can reject or you can eliminate certain set of frequencies. Okay, so that is one application of these resonance AC network. Now we are going to study the equations for series RLC circuit and parallel RLC circuit at resonance condition. That equations are very, very important to you. So please let us see. That is, please note down those equations down while I am explaining. Next, we are going to see all important equations for series and parallel RLC networks during resonance state. Okay, so series RLC network. So this is a series RLC network. R, L and C is connected in series connection. Voltage applied is Vt. So what will be the sum of these? This voltage across R, L and C will contribute the Vt. So that is a voltage relationship in series connection. So Vt is equal to Vr plus VL plus Vc. Right, very simple. Next, we are going to define one term called alpha, and alpha is equal to R by 2L. Okay, and we know that our resonance frequency omega 0 is equal to 1 by root of LC. And as I said earlier, since due to the presence of this resistive element and since the circuit behaves like a harmonic oscillator, there is a damping oscillation due to the presence of resistive element. Okay, so the damping factor tau, damping factor is tau. The damping factor tau is defined as tau is equal to alpha by omega 0. Please note this down. Tau, which is a damping factor, is equal to alpha by omega 0, where alpha is equal to, for a series connection, alpha is equal to R by 2L and omega 0 we know 1 by root of LC. Okay, so if you take the ratio of alpha and omega 0, the damping factor for a series connection is obtained as tau is equal to R by 2 into square root of C by L. So these equations are very, very important. So we'll explain once again. First, defining one term called alpha. Alpha is equal to R by 2L and omega 0 is equal to 1 by root of LC, and the damping factor is defined as a ratio of alpha to alpha and omega 0, and it is obtained for a series connection as R by 2 into square root of C by L. Okay, and also the quality factor for a series connection is obtained as Q is equal to omega 0 into L by R, where omega 0 is the resonance frequency, angular frequency, into L by R is the quality factor for a series RLC network. Okay, and another one term is there. See, we have defined quality factor's general equation as omega 0 by delta omega, right? This is the general equation which we have discussed earlier, where omega 0 is the resonance angular frequency and delta omega is the resonance peak bandwidth. Now, in the question, if they are asking what is the bandwidth, then you have to use the equation delta omega is equal to omega 0 by Q. Don't get stuck there. Use this relation to find the bandwidth. Okay, so this is the bandwidth for a resonance circuit with omega 0 is the resonance frequency, Q is the quality factor. I hope this much equations is clear to you. And I hope that you have noted these equations. Next, moving on to the parallel RLC network, where the resistance, inductance and the capacitance elements are connected in parallel to the source. Okay, there also we know that angular resonance frequency omega 0 is equal to 1 by root of LC, and there we are defining the factor alpha as 1 by 2RC, and tau, which is a damping factor, tau is equal to alpha by omega 0, which is equal to 1 by 2R into root of L by C is the damping factor. Sometimes in question papers they will be asking, from the following equations, pick out the equation for a damping factor for a series network or a parallel RLC network. So you have to know these equations. And also the quality factor for a parallel RLC network is defined as Q is equal to R into root of C by L, and the bandwidth is defined as 1 by R into square root of L by C. So these are the important equations. So if you are preparing for any of the competitive examinations, please note these equations since it is very, very important for you. Okay, so now we are going to discuss some questions from the series and also parallel. That is from the resonance network. We are going to discuss some questions. So the first question that we are going to do is this. What is the resonant frequency of series RLC circuit with R equal to 0.2 ohm, L equal to 4 into 10 raised to minus 3 Henry and C is equal to 2 into 10 raised to minus 6 Farad. So that is a part A. Part B, if the source of constant value 4 volt is set to this frequency, what is the average power transfer to this circuit? Part C, determine Q and bandwidth. So we need to find almost all things. First we need to find the resonant frequency. Since in the question it is not specifically given that whether the angular frequency or normal frequency we need to find. In competitive examination, if such questions is asking, you have to see the options. If it is given in radians per second, it is angular frequency. If it is in hertz, find F, that is take 1 by 2 pi of the angular frequency. Okay. Now we are going to find the part A answer. We are going to find the angular frequency. So it is omega 0 is equal to 1 by root of LC. It is 1 by root of L is 4 into 10 raised to minus 3 into C is 2 into 10 raised to minus 6. And if you solve it, you will get the value as 1.12 into 10 raised to 4 radians per second. This is the value of your angular resonant frequency. I am making it clear. If it is been specifically given angular, find this, or else just look the options. Okay. So here anyway the answer is 1.12 into 10 raised to 4 radians per second. Next, let us do the part B. In part B, we need to find the average power transferred to the circuit from the source of 4 volt. So we need to find P average for part B. We are going to use the equation Vrms square by R. Okay, we are going to use the RMS value of this voltage source or voltage value we are going to take. So we will take Vrms equal to Vm by root 2 in order to find the RMS voltage. Since we need to find the average value of power, we are using Vrms square by R equation. Okay, so what will be the answer? Vrms is equal to Vm by root 2. It is 4 by root 2. So here it is 4 by root 2 square by 0.2 will be your answer. That is 4 by root 2 square is 8. That is 16. 16 by 2 you will be getting in the numerator. So it is 8. 8 by 0.2. That is 40 watts. 40 point something or 40 watts is the power, average power transfer to the circuit. So that is our answer for your option. Your part B. Next, move on to the third part or the part C. We need to find two things in part C. One is quality factor Q and second one is bandwidth. Okay, so quality factor for a series RLC circuit is omega 0 into L by C. Sorry, omega 0 into L by R. So it is, we have obtained it is 1.12 into 10 raised to 4 into L is 4 into 10 raised to minus 3 by 0.200, right? You will get the value as 224 as a quality factor or Q. Next, we need to find the bandwidth. Okay, so delta W we need to find. As I said, use a relation. Delta W is equal to W0 by Q. Okay, so I'm going to use a relation here. This relation, that is 1.12 into 10 raised to 4 by 224. You will get 50.0 radians per second is the bandwidth you are obtaining here. Okay, so the correct answer for bandwidth is 50 radians per second approximately, and the quality factor is 224 is the quality factor. It is not having any units. Quality factor doesn't have any units. It is 224. Okay, so this is how you can expect the questions. Not so lengthy questions you can expect, but if you're going for BARC examination or higher end examination, you can expect such questions. Okay, so this is how you do the questions of RLC networks. Question that we are going to discuss is this. In series RLC circuit, L is equal to 2 into 10 raised to minus 3 Henry, C equal to 5 into 10 raised to minus 4 Farad, and R is equal to 40 ohm. What is the resonant frequency, not angular frequency? Specifically, it is being given. So, we need to find F value. B, what is impedance at resonance? This question we can directly answer without even writing any equations. What is the impedance at resonance? So, while explaining the theory part, I have discussed that during the resonance state, the impedance is purely resistive. So, the value will be equal to R is equal to 40 ohm is the impedance value at resonance. Then C, if voltage amplitude is 10 volt, what is I of t at resonance? Okay, this question also we can directly answer. How can we answer this question? See, the voltage amplitude is 10 volt. So V is 10 volt. What is I of t? So I of t is equal to V by R, right? So during the resonance, the impedance is purely resistive. So current is voltage by resistance. Voltage is 10 volt by resistance is 40 ohm. So it is 1 by 4, which is 0.25 ampere is the peak value of current at resonance state. So we have already obtained two answers directly without spending much time. So these are the two answers for option B and C. Now only we need to find what is answer for the resonant frequency. Okay, so the resonant frequency F we need to find. It is 1 by 2 pi into square root of 1 by LC. That is 1 by 2 pi into square root of 1 is 1. So 1 by root L is 2 into 10 raised to minus 3 into C is 5 into 10 raised to minus 4. If you solve it, you will get is 160 hertz is the value of frequency, which is not angular frequency. So specifically, if find the angular resonance frequency means you have to take omega 0. Otherwise, find F0. That is 1 by 2 pi of omega 0. So these are the answers for this question. So these are some questions which I have included in this video. So I hope the concept of resonance, the series and parallel resonance equation and everything is clear to you now. So this was an exam point of view video for resonance circuit, that is resonance AC circuit. So we have discussed about the RLC series and RLC parallel circuit. We have discussed all the important equations. This video is useful for various examinations, such as if you are preparing for any ISRO technical assistant examination or AFCAT examination or DMRC examination or any examination related to electronics. So there is a lot of competitive examinations in series going to happen for electronics. So if you are somebody who is preparing for any of those competitive examinations, I hope this video was useful for your preparation. If yes, please do give it a thumbs up and also share this video with maximum of friends. And if you want more videos, please do subscribe to the channel and please do tell your friends to follow the channel and subscribe to it. Okay, so thanks for watching and keep on watching.